Welcome to the R Lab for Chapter 4, covering logistic regression, LDA, QDA, and K-nearest neighbors. In this lab, we're going to look at the stock market data using these classification methods to predict whether the stock market is going to increase or decrease. And so we load the data using this library Isler command. The data is in the Isler library. And then we can look at the names in the stock market data. The stock market data contains the percentage returns for the S&P 500 for a period of 1,250 days from sometime in 2001 to sometime in 2005. And so we look at the names of the variables. There's the year, and that's the year of the date that we're looking at. Lag 1 through lag 5. Lag 1 is the percentage returns 1 day previously. Lag 2 is the percentage returns 2 days previously, and so on. Volume is the volume of stock market movement today, and the today variable gives the percentage returns in the S&P 500 today. The direction determines whether the S&P 500 has gone up or gone down. You can look at the dimensions of this data. It has 1,250 observations and 9 variables. We can get a summary of the stock market data. And we look at the year. The year variable goes from 2000 to 2001 to 2005 as expected. Each of these lag days, the min and other statistics are very similar, as one would expect. And the volume tells you the volume in stock market activity. The today looks a lot like the lags, as you would expect. The direction, we have 648 days in which the direction has been down and 602 days in which the direction has been up. For the direction variable, we have 602 days when the direction has been down and 648 days when the direction has been up. And just using that piece of information, if we predicted that the stock market is going to go up every day in a very naive sort of prediction, we would be correct 51.84% of the time. So we could think of that as our baseline. Random guessing 50-50 would be wrong a little bit, but because we know that it goes up a little more than it goes down, and so if we guessed up every time, that would be our accuracy. We can look at the pairs plot for the stock market data, and that takes a moment to update. There's not an enormous amount of information there. We can look at the correlation between the different variables in the stock market using this core command. And if we try to use it on the stock market data as is, we get an error because one of the variables is not numeric, and that's this direction variable. And so we need to look at the correlation between variables that are numeric, and so this command here will get rid of that direction variable. And so here's the correlation between all the numeric variables in the stock market. You'll see there's not a lot of correlation between each, between the different lags, and there's not a lot of correlation between the percentage today and the lags. The only correlation that's significant is between year and volume, and the correlation there is 0.53. And so going forward, we're going to attach the stock market data to our session so we don't have to access so we can access the variables directly. So we're going to plot the volume, and this is the volume on the vertical axis and the index, which corresponds to the year in these different brackets over time, and we can see that the volume is increasing over time, which gives us this correlation here between the year and the volume. Okay, so now we're going to fit a logistic regression model to this data and see if we can predict whether the stock market percentage returns in the S&P 500 is going to be going up or down. So first, we use this GLM command. This is generalized linear model. And we're going to build this generalized linear model and it's going to be direction as a function of lag on the previous 5 days, as well as volume. Our data is going to be the stock market. And this last piece of the command, family equals binomial, tells the generalized linear model to use a logistic regression model. And now we can look at the summary of the fits. Now, this summary contains a little more information than we need. Here's the call. What we care about for the moment is the estimate for these regression coefficients. So these are negative for lag 1 and lag 2. That means if it's gone down on the previous day, then it's a little more likely to go up today. And if it's gone up on a previous day, it's a little more likely to go down. If we look at the p-values for these, the p-value is 0.145, 0.398. Those aren't very high. That's not indicating a strong predictive performance, a strong relationship. And then the p-values, as we go down to lag 3, lag 4, lag 5, are 0.8. So those are not very strong predicting p-values. We can look at if we just care about the coefficients, we can use this command to give us just the coefficients for the fits. We can get a summary of the coefficients. This will give us the summary information about the coefficients. And if we just wanted those p-values, we could do summary coefficients and then get the 4th column in this array. So this here are the p-values for these coefficients. Now, if we want to use this to create predictions of probabilities, we're going to use this predict command on the GLM fits. So GLM fits was this generalized linear regression model using logistic regression that we built up here. And the type response says we want to get the probability of output. So GLM probs, and we can look in our variables up here. This is predictions for the 1,250 days. We're getting the probability that the stock market went up or down each day as predicted by a linear regression model. We can look at our first 10 probabilities. And one of the things you'll notice is the probability doesn't stray very far from a 50-50. We can look at this contrast in direction, and that's telling us that the R has used a dummy variable for direction. And so if we want to know predictions down versus up, we can make a column called prediction. And so this first command repeats down 1,250 times and puts that vector in this variable called pred for prediction. And then this second line here takes that prediction, and whatever that probability is greater than 0.5, it switches that to up. So this glm.pred, we can look at a variable here, and it's predicting up or down whether that probability was greater or less than 0.5. We want to look at how often our predictions were correct. Here we're comparing in a table the prediction versus the actual direction the stock market went. And this is a confusion matrix. So prediction down and stock market actually went down 145 times. Prediction up, stock market went up 507 times. And then you can see the types and common errors that we have off the axis. So the number of times we're correct is 507 plus 145. So our accuracy is a 0.52. That, if we compare it to our sort of naive guessing, it's a little bigger than 0.5184. So that may suggest that the logistic regression is giving us a little bit of predicted performance. But if you're a good data mining, predictive learning person, you'll say, hey, you just trained and tested on the same data. That's not valid. So what we need to do is to create a training data and a test data. And a good way to do that is to create our training data from one segment in time and our test data from the previous interval of time, because that's how we would be using this algorithm. And so instead of taking random training and test splits, we're going to do what's sometimes called a holdout data set. We're going to hold out all the data from 2005. We're going to train on everything before that, and we're going to apply that to 2005. It's sometimes called holdout to emphasize that it's not a random subset of the other data. It's separate data, and it's mimicking how we're going to be applying this learning model. And so what we're going to do is create our training, well, execute this command, which gives us just another way of computing that percent accuracy 0.52, which of course we could turn into percent error by taking 1 minus that. Okay, so we're going to create a training set. So train is going to be the set of all values where the year is less than 2005. So we come over here to our variables, and we see train is a logic variable, and it's a true whenever the year is prior to 2005. And we're going to make stock market in 2005 data. So we take the stock market and we pull out all rows or all observations from the stock market data that are not in the training set. And so to check that, we can execute this dimensions command. So we have 252 observations with our 9 variables. Those 252 observations correspond to 252 days in 2005. So we're also going to pull out the direction in 2005, right? That's our value that we're trying to predict up or down. Now we're going to fit a generalized linear model as we did before. This family equals binomial. That will tell this generalized linear model to use a logistic regression. And we're only going to train on this subset. It's called the training subset. So that's true or false, and true wherever on each observation where we want to be training. So now we fit our generalized linear model, and now we're going to predict the probabilities using that generalized linear model, and we're going to predict it on this 2005 data. Type response means we're predicting the probability for each of those days. And now, as before, we're going to fill in with a vector that's all downs, and then whenever the probability was bigger than 0.5, we're going to put it up in that location. And then we're going to build this table that tells us how often we're correct. So this is for the 252 observations on the diagonal. We can see the instances were correct. So there were 77 times when the stock market went down that we correctly predicted down, and 44 where it went up and we correctly predicted it up. And the errors are in the off diagonal terms in this table. And we can take the mean of the predictions. So this is mean of our prediction equal to the actual direction. And so this mean is a percentage of times we were correct. And it turns out we were correct 48% of the time. That's kind of abysmal. So this is a very poor performance. It's worse than flipping a coin, 50-50. And our error rate's about 52% of the time. That's not very good. Now, one of the things we can try to do to improve our model is to do our logistic regression, but now we're just going to use the lag 1 and lag 2 variables. Up here, we added lag 3, 4, 5 in volume. If you remember, those had lower p-values indicating they weren't as good predictors, and generally we would expect to not give us as good predictive performance. So, we're going to rebuild our model just using the lag 1 and lag 2. Now we're going to predict it on the 2005 data. We're going to do the same thing to fill those in with downs and ups. There's our table that tells us how often we are correct. And here we compute the mean of how often we were correct. So that's about 56% correct. And so we see that using the lag 1 or lag 2 worked a little better than, actually significantly better in our test data than using all 4 of the variables. And we can look at how often we correctly predicted up, and that comes to 8.58. So one of the things you could do is look at what you want to predict and correctly predicting up to determine what days you're going to invest and not invest on other days. And this last line here, this just shows you how to put in predictions manually. So if I want these values for lag 1, 2 observations, and I'm going to make these values for lag 2 on 2 observations, and I want to predict based on those, that command would give me the predicted probabilities of the increase in the stock market based on those. Let's go ahead and build a LDA model, linear discriminant analysis, and that's in the mass library. So we're going to fit our LDA model. You'll notice this looks a lot like our commands for the GLM, the generalized linear model. We're going to use lag 1 and lag 2 as before. That seemed to work better. And everything's set up with our train data set here, so we'll execute that. Here's our fit. And so this tells us the prior probabilities. So in the data that we're feeding into it, the stock market data prior to 2005, the S&P 500 percentage went up 0.508% or 50.8% of the time, and down that percent of the time. This tells us when it went down, the mean these are the means for the different groups or different classes. In the down class or the down group, our mean value for lag 1 was 0.042 and for lag 2 was 0.033. And so on days when it went down, the previous 2 days S&P 500 percentage tended to be positive, and when the S&P on the days when it went up, the S&P 500 percentage on the previous days tended to be negative. That's our observation that we've made already, that when the stock market has been recently going up, it has less likely to continue to go up, and when it's recently been going down, it's a little more likely to go up. This tells us the coefficients of the linear discriminants right here. So we can plot the fit, and for this plot to work, I believe I need to give a little more room to the plot window. So those are the plots of our 2 different classes. Now we're going to predict with this LDA fit that we've created on the stock market data for 2005. When we use this prediction with linear discriminant analysis, it predicts a class, and then it gives us a posterior probability. So this is the probability for each of these classes, and then an X which contains the linear discriminant coefficients shown here. So we're going to create this variable LDA.class, which is the predicted class. And then here's a table that tells us how often we are correct. So down, down, as before, 35 times the stock market went down. And when we predicted down and up on the diagonal terms, 106 we're correct on the up. We can look at the percentage of time we are correct. So this is creating a vector of trues and falses. This double equal sign says check our predicted class versus the actual direction. And when they're equal, we create a true or 1. And when it's false, it creates a false or a 0 when they're different. And we take the mean of that, and that gives us a percentage of time we're correct. So that was about as good as the linear discriminant analysis. You can take a look at some other pieces of information provided. We can look at the probabilities, the posterior probabilities for the first 20 days. We can look at the class assignments for the first 20 days, up versus down. And we could look at one of the options we could do is say, I'm only going to invest on days when there's a high prediction of going up. So this will look at where my posterior probability of going up is greater than 0.9, and we can look at how many days that occurs. And in fact, that never occurs. So the predicted probabilities, as we can see here, don't range very far away from 0.5. So in summary, we created a logistic regression and then linear discriminant analysis models to predict stock market going up or down, and we saw that about the best performance we could get with either of those in our not very deep dive sort of playing around with a simple model, and then we reduced from lag 1 through lag 5 down to lag 1 to lag 2 variables because they seem to have lower p-values. We could get about a 56% accuracy. One more thing we're going to do, we're going to look at a quadratic discriminant analysis on the same data set. A lot of the assignments and functions are the same, except that we use the QDA here instead of LDA. So we'll execute these commands. There's our fit and our class means. We're going to predict our classes. There's our table giving us our confusion matrix. And then when we look at our mean from our predictions, we get a 0.599, so about a 60% accuracy. So in this case, you can see that we get a little better accuracy out of the QDA. This isn't a giant data set. This isn't enough data and enough testing to say that this is true in general about QDA over LDA for predicting the stock market, or that QDA will genuinely give you this type of accuracy. But at least on our training data, the indication is that QDA is working better than logistic regression or linear discriminant analysis. And the expectation is probably because there's covariances are different for our different classes, perhaps. And some of that quadratic or second degree decision surfaces are giving us better separation between our classes and our data. Thank you very much for watching the R-Lab video for Chapter 4 on logistic regression, LDA, and QDA.